Okay.
So let's go with this. And actually, my talk is not about chromodynamics. I use the word chroma in a different sense, but you will see later. In today's talk, I want to present some very interesting statistical model, and I'll start with local Potts model. It's defined on regular lattice, and it is natural generalization of Ising model. In Ising model, we have spin directed up and down at each side of the lattice, but for Potts model, each side can take a discrete values from some set. And common problems for these models is, for example, finding the vacuum state of the system or calculating partition function, which is not easy task even for small lattices. Now let's go to our model. The first difference that we introduce the random lattice, the sites distributed randomly over the area. And here the interaction occurs not only between the closest neighbors, but within particles lying at some distance apart. So we choose distance 1, and also we have some width of interaction delta, and we see that between these interacting particles, there are some particles which do not interact with them. And the one crucial difference of our model comparing to the models on the regular lattices, that for letter 1, the number of neighbors is fixed, it's small, depends on geometry of the lattice. But in our case, it's basically unbounded and can be adjusted by choosing the parameters of the models and obey the Gaussian distributions. And now let's look at the some fields in which models can be implemented. So the two common ones, it's local interaction models. The examples are Ising model, Potts model, the intent model, and etc. And also we have some field interaction, for example, a gravitational interaction, electromagnetic interaction, but also there's a class of model which have interaction at finite distance. Examples are networks model. For example, you can consider the case of neuron interaction when we have neurons connected to each other, but between them there are also neurons with which they don't interact with. Also, interaction finite distance occurs at the problems of imaging processing, and it's very relevant in problems of combinatorial topology. And one of these such problems I want to discuss a little bit more. It's a pretty famous problem of Erdőn Hadwiger Nelson, and it asks what is the minimal number of colors one must use to color the space in such a way that no two points at unit distance are colored identically. For a line, the answer is trivial. It's just alternating strides of unit lengths with deleted point at one side. But surprisingly, already for the plane, that one is unknown. There's also upper and low bounds. For the long time, the low bound was for q is equal to 4. It was established by building this unit distance graph of 7 vertices. It's called Moses spindles. It can be colored in 3 colors. The vertices can be colored in 3 colors in order to satisfy this condition. But recently, one mathematician, using the same method, improved this estimate. He built much more complicated unit distance graphs of about 1600 of vertices, and it can be colored in 4 colors. So the low boundary is 5. What about the higher boundary is the 7. It's achieved by tiling the plane in these hexagons. And uh, what's interesting, the length of the edge of hexagon can take varies in pretty wide range from 1 over square root of 7 to 0.5. And one of our goals was to implement our model to these problems and look what we can get from it. So the basic setup, we have this Hamiltonian. It's basically the sum of interactions between particles. Particles interact when they at the unit distance have the same color. And the goal is using simulations, find minima of energies and corresponding vacuum configurations for two-dimensional random lattice starting from random configurations. It's worth to say that worth to mention that vacuum states of such models have not been investigated before. And the first thing which we should consider is to choose appropriate boundary condition. At first, we used a very natural periodic boundary condition, but then we realized that it's not appropriate here. It turns out that the resulting patterns and the energies depends on the size of the area. So we state with fixed boundary conditions, and this is we just left the belt of particles untouched in the process of minimization. We don't change the colors of them, and it's obvious they somehow influence on particles inside. So we should take some offset from the edge and calculate energy within it. And also one choose the proper expression for the energy. Here on the picture, the red zone, the particles energy of interaction of which is calculated. They interact with each other, but also they can interact if they lie the proper distance with particle at the green zone. The particles at the green zone interact with only with the particles at the red. They don't interact with each other. And we have violet colored particles. They don't contribute to the energy. And in order to energy calculated properly, we should take the interactions of red particles with the factor of 2. With all of this, let's discuss one of the crucial parameters of the model is the average number of neighbors. It's have a Gaussian distribution. It can be adjusted by choosing the appropriate parameters, the size of area, the number of particles inside, the width of interaction ring, and we decided to fix the number by 50. It's enough to investigate the basic properties of the model, but at the same time, it allows to make calculations in reasonable time. Now let's move to discussing the minimization algorithm. The choice of this algorithm is a very tricky one. First, we used very simple greedy algorithm, which just looking for the neighbors of the particles with least represented colors and change color of particles to it. But the problem with this that we end up at the state of local, not global minima. So it's this big problem. And in order to overcome this, we devised and implemented simulate annealing algorithm, which allows the system to take the state with the higher energy. So basically, we start from random configuration, calculate its energy, choose temperature reduction function. It's very important here to choose the proper one, and also choose appropriate parameters, optimal parameters. And next, we go through all particles in random order, and for each particle, randomly change color. If energy decreased or state unchanged, then of course accept new configuration. But here there comes difference with the greedy algorithm. Here we have probability, this probability to accept configuration with increased energy. And as temperature reduces, this probability goes down, and eventually we find yourself up at the state which have much higher probability of being global minima states comparing to the greedy algorithm. And let's look at the typical minimization process. Here is the random configuration for 6 colors. Here we start from temperature of 10. We use linear reduction function. And here just the diagram of ratio of colors. So let's start. The energy calculated between particles which lie inside this ray area, but also they can interact with the particles inside the green one. So let's go. First, we see some fluctuations as temperature decreases, energy decreases, but not so quickly. The ratios almost don't change, but here we start to observe quick clusterization, and the two colors are falling down, but quickly restore, and some regular pattern emerge. And as temperature decreases, the energy decreases too, and eventually it gets zero. So this is how the minimization typically goes. And here the results for different number of colors. For two colors, the configuration is trivial, but it gets much more interesting for a higher number of colors. For 3 and 4, we got almost ideal regional hexagonal patterns, but even for higher colors, we still see the hexagonal patterns. For 6 and 7 colors is just a juxtaposition of regular lattices of each color, so they just shifted relative to each other. And one of the main tasks which we wanted to investigate, for which number of colors we will get the configuration with the zero energy. In order to answer this question, let's look at the histograms of energy. At the top, we see the comparison of 5 and 6 colors, and we see that the distribution of for 5 colors lies pretty far from zero. Uh, at the contrast, for 6 colors, we near 0 point, and in order to look more closely, let's zoom in and compare 6 and 7 colors. For 7 colors, we got zero energy in approximately 80% of cases, and this was good result and indication that our model and algorithm works properly. From the case of Hadwiger-Nelson problems, we should get the zero energy for 7 colors, but unfortunately for 6 color, it's much more unclear. We got zero energy at approximately 1% of configurations. There's one pretty close to zero, but for now, it's hard to say whether 6 color is enough for the energy of vacuum configurations to be zero. Some additional study should be provided. And now let's move back for one slide and look at this picture for 5 colors, and we can clearly see the some deficiency of fifth color, and this is not an optical illusion. Indeed, the fifth color is reserved much more. So basically, we observe the breaking of color symmetry in effort of keeping geometric symmetry. And in order to capture this effect, let's see how the ratio of minimally represented color will change when we increase the size of the area. So if we observe this effect locally or globally on the whole area. Let's look at the graph. Here, this dependence of the size of the area for 5 colors, and the initial curves, it's how things go for initial configuration. It's no surprises. The ratio is close to 1. It's expected. We randomly generate points and colors. But for minimized configurations is much less, and doesn't strive to too close to this curve, um, and basically it's uh, uh, it doesn't changes with the growth of the area. So effect is global. In contrast, let's look at the picture for three colors. In this case, these curves go along for initial minimized, and we don't see this effect at all. In order to investigate is a little bit more. Sorry, one more slide. This is the summary picture of this effect, and we see that this symmetry breaking occurs even for 4 colors, but in much less extent than for 5 colors. For 5 colors, it's profound. And in order to observe, to study this effect more, let's look how this ratio changes during the process of minimization. Here we start with initial temperature for 6 colors at the top picture. This ratio fluctuates, and when clusterization becomes, we see a rapid fall in this value, but even quicker rise, but the ratio didn't restores for previous values. But for 5 colors, we see that after the falling, there's some attempts to restore, but eventually the number of particles with minimal colors falls down even more. So yes, this is a very interesting effect, and this is just an illustration of how things can go. We didn't investigate how such effects depends on the parameters of simulated annealing algorithm. So probably it's scope for future work, but our suggestion can be that probably for other colors than 5, we can find an optional parameters when this ratio will restore to the initial values. And this is a summary picture, and we can see that for smaller number of colors, the effect occurs earlier. This is for 5, 6, and 7. It tries to restore for uh, 6 and 7 colors, but for 5s, it's not. This brings me into conclusions. We studied the vacuum states of non-local Potts model on random lattice by implementing simulated annealing algorithm, and it has proved to be efficient. And I think the main result that for 5 colors we didn't observe states with zero energy. It can be the indirect evidence of that one should search the solution for Hadwiger Erdős-Nelson problem in 6 and 7 colors. And the case of 6 colors is much more tricky. In order to study this, one should first choose optional parameters of simulated annealing algorithm, and eventually go to the continuum limit. But this is a hard task. It can be various approaches. It's not obvious whether approach prefer. So this is a theme for different work, and also interesting to observe the breaking of color symmetry effect, which is the most prominent for Q is equal to 5. So that's all. Thank you for your attention, and questions, please.
Thank you. Alexander Nozik has question.
Yes, the question is that at the beginning you showed several possible applications for your model, but as far as I understand, all of them require 3D lattices, and the number of dimensions could be crucial to this work. Have you tried to do it in 3-dimension, not in 2-dimension?
Thank you for the question. No, we haven't tried this yet. Actually, even for 2-dimension, the task is pretty complicated in the terms of computing. So we haven't tried.
And do you have a code for this simulation published anywhere?
Not yet. We write an article and soon plan to publish it at arXiv. So
yeah, the article is okay, but you can't try to solve computational problems without the code. So are you planning to publish the code itself?
We haven't considered this question. I think we didn't have such intentions, but maybe if someone will be interested in, so we can.
Personally, I strongly suggest you to publish the code, because there are a lot of those articles that they say that we can solve this problem due to computational problems, or there is some complicated algorithm which could not be reproduced by anyone else because there is no code. So I do not think that those articles without code provide a lot of insight for future work.
Yeah, so I got your point. Thank you. Yeah, indeed. You mean that anyone who want to check our results? Yes.
No, not to check results, but to improve. For example, you say that you have computational problems, then problems could be solved. For example, see yesterday talk by Roland. Some things could be solved by just involving different tools.
Actually, sorry for interrupting, but maybe you can even tell us a bit more about your implementation, especially the optimization steps. That will be quite interesting. A couple of words. Thank you.
Yeah, actually, I think the great optimization of algorithm to this point was the changing of algorithm to simulate annealing, and we haven't optimized this algorithm yet. So we had some tries. We tried different temperature reduction functions, some initial parameters, but we haven't done yet some systematic study. And I think we're planning to do it. It's very important to get more precise results, the more relevant results. But I think the purpose of the talk was to show that smooth annealing algorithm is appropriate in this situation and gives some field to further improvements. So for now, I think there's no special advices about optimization. Sorry, was your question?
I was asking a bit more about the actual implementation, what kind of tools you used, like at least in which language, for example, you implemented it. Just yeah.
No, I haven't. We haven't used some particular tools. So the program is minimization is written on C++. We didn't use some libraries with algorithms, particular libraries. So no, so probably no.
Okay, yeah. So obviously, if you can put your code somewhere on GitHub or somewhere, it will be really nice to have a look, because it's very interesting. It's a very interesting problem, of course, and it will be, of course, nice for people to reproduce both, and then maybe have suggestions, as Alex said, to what you've done, guys, because it's very interesting. Thanks.
Okay, thank you.
Okay, no more questions. Let me ask you a simple question. Do you have imagine any application of this algorithm in 2D? Because everything which you mentioned were referred to 3D, and in 2D, do you know the tasks which could be?
Thank you for the question. It's a really hard one. When we designed this model and studied it, we were trying to find out some physical applications, but turns out it's not easy to do. And for now, I say probably this model mostly can be used in some of these combinatorial topology problems. So I don't have a direct answer on your questions. It's the model is really interesting, but find in some physical application it's hard enough.
Okay, thank you. If there are no more questions, we can let the next speaker start.